In this video, we'll be going over the three most important heat transfer equations when designing evaporators. We will be briefly exploring the term boiling point rise and why it's important, as well as introducing ourselves to evaporator economy. To begin with, the first heat transfer equation we're going to look at is Q equals mCp delta T. Q is the heat transferred in joules, m is the mass in kilograms, Cp is the specific heat capacity of the liquid at constant pressure measured in joules per kilogram Kelvin, and delta T is the temperature difference in Kelvin. The second heat transfer equation is Q equals UA delta T. Q is the heat transferred in joules, U is the overall heat transfer coefficient measured in watts per meter squared Kelvin, A is the area in meter squared, and delta T is the temperature difference in Kelvin. The third and final heat transfer equation we're going to look at is Q equals m lambda, where Q is the heat transferred in kilojoules, m is the mass in kilograms, and lambda is the latent heat in kilojoules per kilogram. These three heat transfer equations are incredibly important to know and understand, especially when designing evaporators. A more concentrated solution will have a higher boiling point compared to the boiling point of the pure solvent. For example, a pan of salt and water will have a higher boiling point than a pan of plain pure water. This is because the solute particles in the solution causes the vapor pressure of the solvent to decrease. This phenomenon is known as the boiling point rise, and this is an extremely important characteristic to consider when designing evaporators. Essentially, the boiling point rise, or BPR, is the difference in temperature between the boiling point of the solution in the evaporator and that of water. The boiling point rise of a solution is always unique to that particular solution being heated. The reason why the boiling point rise is such an important factor when designing evaporators is because the boiling point rise directly affects the delta T value in the heat transfer equation Q equals UA delta T. As a result, this will directly affect the heat transferred in the evaporator. Here we have an example question regarding boiling point rise. The question states, at atmospheric conditions, a 25% solution of sodium chloride boils at 381 Kelvin. Work out the boiling point rise. As we just mentioned, the boiling point rise is the difference in the boiling point temperature of the solution and that of water. The solution in this case is sodium chloride, and we're told in the question that the boiling point of sodium chloride is 381 Kelvin. We're also told that the pressure is the same at atmospheric conditions. Since we know that the boiling point of the solution is 381 Kelvin, and we know that the boiling point of water is 100 degrees, which is 373 Kelvin, the boiling point rise will therefore be 381 Kelvin minus 373 Kelvin, which equals 8 Kelvin. The second part of the question asks us to determine the overall temperature difference if steam at 889 Kelvin is used to concentrate the solution. The answer to this would simply be the temperature of the steam, which is at 889 Kelvin, minus the temperature of the solution, which is 881 Kelvin, which gives us a temperature drop of just 8 Kelvin. The boiling point rise of a solution cannot be calculated from physical property data alone. Instead, an empirical rule known as Duhring's rule is used to estimate the boiling point rise of a solution. Duhring's rule states that at the same pressure, the boiling point of a given solution is a linear function of the boiling point of pure water. As a result, when you plot a graph of the boiling point of the solution at various different concentrations against that of pure water at the same pressure, it produces a straight line graph. Here on the x-axis we have the boiling point of pure water, and on the y-axis we have the boiling point of the solution. And we can see the plots here at various different concentrations. The green line represents the solution at 0% salt concentration, or in other words, it represents pure water. The blue lines here represents the solution at various different salt concentrations, which, as you can see, at higher salt concentrations, the boiling point of the solution increases due to the reduction of the vapor pressure of the solvent. Eventually, as the concentration of the solution is increased further, it will reach its saturation point, which is represented in the red line here. One method of assessing the performance of an evaporator is using evaporator economy. This equation compares the quantity of the vapor produced against the quantity of the steam consumed. The value is normally expressed as a percentage. Since single effect evaporators are not very efficient, you would typically expect these systems to have economies less than 100%. On the other hand, double and multiple effect evaporators can often have steam economies of greater than 100%.